Okay, so go ahead and label this. We're getting into the inverses. So for 8.1, they kind of break them into segments. We're going to do inverse sine, inverse cosine, and inverse tangent. So I'm going to go ahead and give you a second just to get that labeled, and then we'll start looking at kind of what's going on here. Okay, so I want to go back to algebra for a second before I explain the trig thing. And let's go back at looking at things that we're already familiar with. So let me show you a function. Let's say we have f of x is equal to x squared. And let's say our domain is everything, because that's how we normally think of it. And so in that case, you guys know what x squared looks like. It looks like this. Do you guys kind of remember? There's your f of x equals x squared. Okay, now, there's nothing wrong with that. It's just that sometimes we want to change the way that we do things. And so we're used to kind of taking a function, we plug x into the function, correct? And we get out what? Y. But sometimes you want to reverse that. You actually want to have your result be the x, not the y. So you're switching, instead of having coordinates xy, you're having coordinates yx, in essence. But in order to do that, in order to have what we call an inverse where you can swap the coordinates, do you guys remember that the function has to be 1-to-1? Does anybody, probably, I don't know if you remember it or not. 1-to-1 means it has to pass horizontal line test, which means when you start running horizontal lines, it can only hit one time. And you can see with this one what happens. It's hitting twice. Do you guys see it? So this is what we would call not 1-to-1. So there's no inverse. It can't have an inverse if it's not 1-to-1. All right, and that's a problem because obviously this section for us is on inverses. So what do? So what we do with this is we take the same function, and just like everything else in math, we force it. We make it work. And so we force it by, there's different ways you could restrict it, but instead of maybe doing the domain of everything, I could just run the domain from 0 to infinity. So visually, it would just be this side. Do you guys agree with me? Now, it's still the same function. It's still x squared, but we restricted the domain. Do you guys kind of see that? Now, the reason that we do that is now when you run horizontal line test, how many times is it hitting? Just once. Does that make sense? So with that restricted domain, this function is 1-to-1. So this one would have an inverse, and that's how we get an inverse for x squared. We just put a restriction on it. Make sense? Kind of get the general gist of what's going on there. We're not going to test on that, but I want you to have an idea. Okay, well, you guys already know that all the trigonometric functions are periodic, which means what do? They repeat. So when you look at a trig function, sine and cosine kind of look like this, right? They're definitely not 1-to-1. Do you guys agree with me? Or even tangent, what does tangent do? It kind of does this, right? Repeating, still what? Not 1-to-1. So none of our trigonometric functions under their standard domains are 1-to-1. They're just not. So what they did is they put all these restrictions in with a little bit of insight of taking certain things into consideration. And once they restricted them, then they were able to get inverses for all the trig functions. Okay, now before I show you how they restricted them, I want you to get the train of thought, because I want you to think of this really as one way. With trig functions, what we've been doing is we've been saying, okay, we're plugging in the angle. Isn't that what we've been doing? Like plugging in pi 6 or 360 degrees or whatever into our trig function. And so then we've been getting out basically some ratio. Do you guys agree, like square root of 3/2 or root 2/2 or 1? Does that make sense? It's kind of, we've been getting some number out of it. All right, now, of course in trig, I think you guys can understand this. Sometimes we want the ratio, but sometimes we want the angle. Like if you're landing a plane, really the angle is what's so important. Are you guys kind of following me there? So you need to get access to this angle that's kind of stuck inside. So what do? You reverse it by getting an inverse. So with the inverses, what you're doing is now you're plugging in what? The ratio, and I'm going to put the notation in. Do you guys remember? Do you see that little -1 I just attached? Do you guys remember that means inverse? So that's inverse notation. You plug in the ratio, and what do you get out of it? The angle. So always think of your inverses as your angles. You're getting an angle as your answer. Now, a couple of other things. That's one notation. So one way you'll see this is your trig function raised to the -1. That's one way you'll see the notation. There's another way, and I just want you to be aware of it. And they use it a lot in calculus. I still like the inverse notation as it is there, but you will see this. They'll sometimes say arc trig function. So they'll say arctan or arc cotan of whatever the ratio is equals theta. And that is a legit, so the ARC and then whatever the trig function is, that is another notation for inverse. So just remember the main point in this, we have to restrict the graphs to make them 1-to-1 so that we can have an inverse. The reason in trigonometry we want access to the inverses is to give us access to the angles. We want to find out if with this ratio, what angle do we need, right? That's kind of the goal. So we've got to be able to reverse it, but that means we've got to remember all these restrictions. Okay, I'm going to show you some of the pictures. So the first one I think they give you is inverse sine. So let me show you the visual piece first, and then I'll give you the definition. This is the part that you guys have to know. It comes back in calculus, so it's a good thing to go ahead and just try to get it down. I'm going to go ahead and move down, and I want to show you the picture. This is inverse sine right here. Do you guys see the graph? Of course, if you run horizontal line tests, what's going to happen? It's not going to pass it. Does everybody see it? So notice what they did is, in order to get the access to the inverse function, they restricted it to this blue part here. So they said, oh, we're only going to take this part. Do you guys see it? And so they restricted it between -pi/2 and pi/2. Do you guys see that all right? And if you just take that blue part, now remember this is an inverse sine, this is the original trig function, they restricted it, then it is 1-to-1. Do you guys see it? Just the blue part right there, which is actually this graph right here. Are you guys okay with that? And so by restricting sine, now you can find inverse sine. Now inverse sine will visually look different, but I just want you to see that the restriction had to happen first to make it 1-to-1. And then we can get access to the inverse. Are you guys good with that? Okay. Now, I'm going to do this just so you can see it. Right here, if you just restrict the graph, let me come back a little bit this way. So here's the restricted graph. Couple things I want you guys to see on that restricted graph. Do you see here that the domain for sine of x, or let's do sine of theta because that's going to make more sense to us. In this case, what's the domain? Your x would be your x's, right? Do you guys see it's running from where? -pi/2 to pi/2. Does that make sense to you guys? And now let's look at the range. I have a reason for showing you this. The range, the y's would be -1 to what? 1. Are you guys okay with that? Now, we just got through saying that the inverse swaps the coordinates, right? So if you look at now the inverse function, and they don't use y, you guys, just to make it real confusing, they like to use x. They actually like to put x in here. So maybe I should write it like this just to... Well, just because I know how they're going to write it on the next page. I know it's confusing. Just don't let it throw you off. It's what they do. Or no, I'm wrong. I'm wrong. No, I was right. Yeah. Yeah, okay, sorry, I was right the first time. Okay, all right, now, when you do an inverse, because you switch domain and range, it's going to switch domain and range on the graph of the inverse function, right? And so what happens is your domain becomes the range of the inverse. Are you guys okay with that? And so the domain would be what? Negative 1 to 1, right? Because, and I'm going to give you this formally in the book, but I just want you to kind of see it, right? Because if you're swapping coordinates, the x becomes the y, and the y's become what? The x's, right? And then your range becomes the domain of the inverse. So it becomes negative pi over 2 to what? Pi over 2. Hang on. I didn't do this right. I'm really on a roll today. Let me rewrite this. Domain of the inverse equals the range of the function. Having a hard time getting my notation good. Or written well. Okay. And then the range of the inverse equals the domain of the function. Okay, better. All right, has everybody got it okay? You get the big picture of it, just enough. Then it just becomes memorizing it. Once you know all the trig functions are going to be restricted, you know your domain and range then are going to swap from the restrictions. You're good to go. You just need to know what the restrictions are, and then you can work with them. And remember, the whole goal is to get access to the angle. That's what you're after here. Everybody got it? Okay. Now, the book gives you a definition one way, and then all the examples are done the way I wrote here. So we're going to change it to where it matches the examples, okay? Because the whole point of the inverse is to give you access to the angle. So we really want to stress that. So we're going to take their definition, but we're going to change it to match their examples in the book, okay? So that it matches with everything else that we're doing. Is everybody okay if I clear this? Everybody got this written down? Everybody's all right? Okay. All right, so now that you kind of get the big picture of it, I do want to move on. Let me go to the next page in the book, and we're going to slightly change this. I just want you guys to see how they're using y here, but then when you come around down here, they immediately change it to what? Thetas. Does everybody see it? And so we're just going to change it at the very beginning. I don't want you to learn it a different way. So what we'll do is we're going to just rewrite this top part. Maybe I should just give them, you know what, just let me write them differently. I already did it, but I'll do it again. Let's just do, I'll just do it myself. Okay, so this is our first one. So this is inverse sine. And so you'll have theta is equal to the inverse sine of x, which is what I gave you before, remember. Okay, and that means, now think about that for a second. This is something really cool about inverse functions. So we know the inverse is great because it gives us access to the angle. But what if you want to go back to the original function? You can. But what do you have to do? So if you want to go from inverse sine just back to regular sine, you can go back, but you have to do what? Swap the coordinates. Does that make sense? So instead of plugging in x, what are you going to plug in? Theta, or the y, and then you'll switch it and you'll get the x on the outside. Does that make sense to you guys? Everybody's got that all right? So you can always go back to the regular trig function. You just have to swap the coordinates. Put the theta back in is what you're plugging in. Make sense? So I just changed these two to get back. Are you all right with that? Okay. Now, the only thing is, you can get the regular trig function back, but the restrictions still hold. You can't change those restrictions because your original start out was an inverse. Anytime you start with an inverse, there's going to be restrictions on the range, period. All right, so here they are. Now, you already know because you visually saw it. This is going to mean that your x's, so this is going to be the domain part for the inverse, is going to be -1 to 1. And the book will write it like this. It'll say x will be between -1 and 1. But it means the same thing. Why? Because you know your original function's range was between -1 and 1, right? So it's going to swap over for the inverse. Does that make sense? Okay. And it also means that your theta, your range, so your theta will be between -π/2 and π/2, inclusive, meaning you include the ends, or sometimes they'll write it like this. Means the same thing. I just want you to have both notations. And this is the part right here that you've got to have. You got to get that memorized. The good news is, you guys, at the end of the day, we have two families we have to memorize. We have what I always call the 1 and 4 family, and we have the 1 and 2 family, but we're not quite there to put it all together. I'm going to visually show you this, though, because I'm a visual person and I like to visually see it. So visually, what this looks like, here's 0. You agree with me, right? What is this? π/2. So this is 0 to what? π/2, because you'd be moving counterclockwise, right, for a positive angle. Negative angle, though, would move what? Clockwise. So it would be like this. Do you guys see it? And so look what they've done. The only two quadrants that you have available when you're dealing with an inverse is quadrant 1 and quadrant what? 4. Does everybody see it? So there's only two quadrants that you've got. Now, with inverse sine, you can include all quadrantals, because you can include the 0, because it's in there. You can include π/2 because it's closed, and you can include what? -π/2. So you have all your quadrantals available to you. Not all of them do. And then you've got quadrants 1 and quadrant 4. Make sense? So really we've got, I'll put it in blue, we have this, and we have this. All of that's available to us. Make sense? Because of the equal to's on the end. All right. Okay, so far I'm like, well, this is not the end of the world. We've got to know the theta is between -π/2, π/2, which means we have quadrant 1 and quadrant 4 available. Now, they were smart in what they did, because we're going to go back to the original function for a minute. Sine's positive in quadrant 1, isn't it? But what is sine in quadrant 4? Negative. So notice that they made sure to take a positive case and what? A negative. Now, the good news is all of your inverses include quadrant 1. So we know the positive case means quadrant 1, no matter what. The question is, where's the negative case? The negative case will either be in 4, like in this case, or it's going to be in 2. And I'll show you that in a minute. All right, everybody got it? Okay. Now, let me show you an example. So I'm going to kind of jump around a little bit, but I want you to see what's going on. So here's what you're going to kind of hear when you see examples of this. So this will say, find the exact value of the expression, which we're used to, so don't approximate it. All right, and we're going to work with inverse sine to begin with. We're going to look at number 15. They want us to find the inverse sine of 0. All right, the minute that I see an inverse, I start thinking restrictions, and I think, oh, I know I'm looking for what? An angle. How do I know I'm looking for an angle? Because I'm looking for an inverse. Does that make sense? And then the next thing I immediately do is, because it's inverse sine, I know theta has to be where? Either here or there. Does that make sense to you guys? So I kind of visually put it where I can see what's going on. Everybody okay with that? So we're looking for an angle. We know our angle for inverse sine has to be between -π/2 and π/2. Make sense? Now, I want to kind of throw something out there so you guys can see it. Remember, we only have our known points either on the unit circle or from your triangle are either like square root of 3/2, 1/2, right? Or root 2/2. Those are the only exacts that we know. Am I right? Is 0 any of those? It's not root 2 over 2. It's not a half. It's not square root of 3 over 2. Do you guys see it? So it's not coming from the 30, 60, or the 45. Following me there? So if it's not coming from those and it's an exact, it's got to be a quadrantal. Are you guys kind of with me there? So my next step is, let me fill in these points. We know that's 1, 0, correct? This point is 0, 1, and this point is what? 0, negative 1. And now which coordinate on the unit circle do we associate sine with? Just the function sine. Y. So remember, you can always get back to the original function if you want to by swapping your coordinates. So just take a real quick look and say, where is sine going to be 0? It wouldn't be at pi over 2, because what would it be at pi over 2? 1. It's not negative pi over 2, because what would it be at negative pi over 2? So where does it have to be? At 0. Do you guys see it? 0 radians. Make sense? And so you would say, well, then the angle where that's going to happen, what would theta be? It would be 0. Remember, if you don't put the degree symbol, it would mean that you're in radians. If you guys want to use degrees, that's okay. We tend to use radians a lot, but you can use degrees if you'd like. Just make sure you put your degree symbol on there. How's that? A little wonky, right? Because you're changing gears a little bit. But the good news is, remember in trig, there's only a handful of things you can get an exact for. So if it's in quadrant 1 or 4, it's got to be square root of 3 over 2 or negative square root of 3 over 2. Root 2 over 2 or negative root 2 over 2, or a half or negative a half. If it's not, it's one of the quadrantals, and so it's going to either be 0, pi over 2, or negative pi over 2, and you just got to figure out which one. Make sense? Okay. All right, you want to do another one with sine real quickly? Okay, so let's do, we'll do 3. I'll try to cover as much as I can here. All right, so let's look at question 21, same exact instructions. And for this one, we have the inverse sine of root 2 over 2. And I'm going to repeat this. I know I'm looking for an angle. How do I know? It's an inverse. And because it's inverse sine, we know we've got to be between these two values. So I'm just going to copy what I did up here because it's exactly, oops, it's exactly the same. Everybody with me there? Okay, now this is different, you guys, because this is not a quadrantal. How do I know it's not a quadrantal? Because your y coordinates for sine are either 0, 1, or what? Negative 1 on the quadrantals. It's none of those. Everybody see it? So root 2 over 2, do you guys remember where is that coming from? It's going to be the 45. Does everybody see it? Are you okay? Now, if you've forgotten, either, if you know, I think this is one advantage to the unit circle is because you can pull those points up right away. You know that's 45. But if you're a right triangle person, you can still do it. Just have your two triangles drawn at all times, and then you'll be able to locate it. It's not a big deal. That's if you're like me and you're not having trouble drawing them today. So here's your 45. 45. This is 1, 1, root 2. We'll make this the 30, 60, square root of 3, 1, and 2. And then you can use your SOHCAHTOA to get it. Let me put it off to the side here. And so since we're concentrating on sine right now, you could see that it would have to be what? This one that would give you, it's the only one that'll give you a root 2. Make sense? Is everybody with me? Okay. So you know the reference angle in this case is 45. Everybody good there? Okay. Now, the deal is we got to pick a quadrant. We know that inverse sine is visually here or here, correct? But in order for it to be in quadrant 1, you would need this ratio to be positive because then that's what sine would spit out, would be a positive. Does that make sense? So is it in quadrant 1? Yes. If they turned around and they made that negative, where would it be? It'd be in 4. Does that make sense? So just look at your ratio and see if it's positive or negative. If it's positive, it's going to be 1. If it's negative, it's going to be 4. Does that make sense? Yes.
So what if it was negative?
I'm going to show you one next example. Yeah, you would just move it to the negative. Yep, that's exactly, and we'll talk about that. That's actually a really good question. So just hold on because I want to introduce that. That's a very good question. Okay, so what's our theta? Pi force would be in quadrant 1. Am I right? 45 degrees is pi force. Make sense? Seems easy enough? Okay. All right. It's just the restrictions. That's the only thing. All right. I'm going to move over. I'm going to go ahead and just take actually, let me just take everything with me because I know we're going to need it anyway, since we're still dealing with sine. Okay. So here's this. Or you can just use your points on the unit circle, or I'll bring the triangles over. It doesn't matter to me. Okay, so now we're going to look at the last one we'll do with sine for right now is question 24. And we have the inverse sine of, we have negative square root of 3 over 2. So again, I know I'm looking for an angle. How do I know that again? It's a what? Inverse. The minute you realize you have an inverse, you should get an answer that is an angle. Right? Okay, is it a quadrantal?
Yes.
What do you think? What would your quadrantal y values be? 0, 1, and negative 1. But that's not what your ratio is, right? Does everybody see it's not 0, it's not 1, it's not negative 1? Make sense? You following me? Okay, well, if it's not 0, 1, or negative 1, it's either coming from the 45, the 30, or the 60. Am I right? It's not the 45 because to be 45, you need root 2 over 2. Makes sense? So really, it just becomes, is it 30 or is it 60? So I'm going to kind of flip back real quickly and mentally think of just sine, not inverse sine. Let's look at 60 real quickly. I'm going to, of course, pick the right one. It's not 30. Do you guys see why? What would 30 be? 1/2. Make sense? It's got to be what? The 60, because 60 for sine would be what? Root 3 over 2. Does that make sense? Everybody's got it. Okay. So I've determined the reference angle is 60 degrees, which I know in radians means a denominator of 3. Is everybody with me so far? Now we got to pick the quadrant. Since it's not a quadrantal, it's in a quadrant. We know inverse sine is either in, we talked about this, 1 or what? 4. Which one do you guys think it's in? Good. How'd you know it was in quadrant 4? Yeah, that negative right there is the giveaway. Make sense? Now, what makes this hard is that you have to keep in mind, not only do you have to know the quadrants, but you've got to know the restriction here. I actually think this makes it easier, but I want to point a couple things out to you. If you want to get into quadrant 4, you've got to move clockwise according to the restriction. So your answer would actually be negative pi over 3. Does everybody see why that is? Because it'd be negative 60, right? So your theta would be negative pi over 3, because we know 60 degrees means a denominator 3 in radians, and we write it as what? Pi thirds, correct? Or negative 60 degrees, however you want to write it. The question, or sometimes what people want to give as an answer, is 5 pi over 3. Now, why would people want to give 5 pi over 3 as an answer? Because it's in 4, isn't it? It's in 4 and it's got the right reference angle. Yes? Why can't I give 5 pi over 3 as an answer? Because the restriction. Look at it. 5 pi over 3, you'd have to go around like this, wouldn't you? And then you're getting into this territory over here that you're not supposed to go into for an inverse. Do you guys kind of see it? And so that's why this is no good. Even though it's the right quadrant and it's the right reference angle, you're going beyond the restricted graph that you had available. Does that make sense to you guys? So you can't do that. So you want to make sure anytime, this is a nice thing, you guys, Anytime you're in 4, use a negative. That's it. So use what you would use in quadrant 1, just make it negative. It always works that way no matter which one of your family that you're using. If 1 and 4 is the family, for 4, make it negative. At least that always matches, okay? Everybody got it? It's all right? Yes.
So when this game was used, reference angle only for it? That's it?
Yeah, reference angle quadrant. That's it.
No, I'm saying, can we use it because you know you can go around, even though 5 power 3 is reference to negative power 3.
Right.
So can we just use the reference angle as the answer?
Basically, except you have to attach the negative
So,
because that puts you in the right quadrant. Yeah, so it's basically the reference angle with making it negative to get into 4. Yeah. So that is the correct answer. All right, is everybody good there? Okay. Now they're going to bring in inverse tangent. Inverse tangent is also 1 and 4, but it is slightly different, and I'll show you visually. And actually, since I'm giving you the stuff anyway, I'll just write it out. So let me get it over here. Or I'm sorry, they bring in inverse cosine. I don't want to bring in inverse cosine yet. We're going to bring in inverse tangent because they're both 1 and 4. And then I'll bring in inverse cosine. Okay, so inverse tangent is on page 614 in the book. So we're going to call this rule 2. And again, we're going to use theta. So we have theta is equal to the inverse tangent of x. Means, remember, you can always get back, because we're switching back and forth between the inverse and the regular function all the time. You guys can kind of see when we're working these problems. You can always get back to the original by just what? Swapping the coordinates. Make sense?
number 2.
This is number 2. Now, as far as your restrictions go, for your domain, it will actually be all reals. So that means x can be anything. That's how the book writes it. And then for the range, it's going to just be slightly different in that you can't include the 2 end quadrantals. So with inverse sine, remember you could include the negative pi over 2 and the pi over 2. You can't do that with inverse tangent. And this is the part you kind of want to memorize. Now let's go ahead and get our visual here. So we're saying here's 0, here's pi over 2, and here's negative pi over 2. Do you guys agree? So you're going to here, and then you're going to here. So you're still using 1 and what? 4. Is everybody okay with that? But the only quadrantal that you can use is at 0. Does that make sense? Because you're excluding negative pi over 2 and you're excluding pi over 2. Make sense? So it's just a little more restricted on the range. Are you guys all right there? Okay. All right, so right now in our 1 and 4 inverse families, we've got inverse sine and inverse tangent are kind of housed under the same umbrella. Makes sense? Which is nice. The only thing we have to keep in mind is that these 2 quadrantals are not included. Other than that, it's really just like inverse sine. Very similar. Okay, now we're going to make sure we can work problems with inverse tangent just like we could work problems with inverse sine. So let's go through, let's look at a few of these from the text. It's going to be the same thing. They want us to find the exact value of the expression. Does everybody have everything written down here? Okay. All right, and so let's see. Let's take a look at, let's do question 20 to start. So we have the inverse tangent of -1. And I'm going to go ahead and just bring over this and my 2 triangles because I know I'm going to need them. Or if you know your points on the unit circle, that is completely fine. Okay, now, the first thing mentally you want to do and that you should know is you need to know you're looking for an angle, and the key is that you have an inverse. Because it's inverse tangent, this is the part you have to memorize. You have to know that your angle is restricted between what? Negative pi over 2 and pi over 2. And if you're like me, I like the visual side here. That's just how I operate. Now I'm going to go ahead and I'm going to plug in this point. We know that's the point what? 1, 0, correct? I should have just copied that one. That's okay. I'm not going to bother putting points on the top and bottom because we can't include those quadrantals. All right, so the ones on the y-axis I'm not even going to bother with. So only that one quadrantal is available to us. All right, now taking a look, we know that when we're dealing with negative pi over 2 to pi over 2, we're getting inverse tangent of 1. And I don't know if you guys are as familiar with your points with tangent as you are with sine and cosine. So I don't know, we'll see here. So I know it's not a quadrantal, and the reason why I know it's not a quadrantal is that if you were to look at the only quadrantal that you have available, isn't tangent y over x? And so it would be what? 0 over 1, which is what? 0, which means that this right here would have to be a 0. Does that make sense? So it's not 0. That's not the case. That tells me if it's not 0, it's got to be coming from one of the two triangles. It's either the 30, 60, or the 45. Do you guys see it? I'm going to start with the wrong triangle first. If you were to try 60, it would be square root of 3 over 1. Does everybody see it? That's wrong. If you tried 30, what would it be? It'd be 1 over square root of 3 or root 3 over 3. Because you're doing the TOA, remember, opposite over adjacent. What about the 45? It'd be 45 because that would be 1 over what? 1. Opposite over adjacent. How are you doing? Okay. So I've made the determination. I'm like, all right, I know the reference angle here is what? 45 degrees, which means a denominator 4 in radians. Makes sense because I think that's what MathLab's going to want. All right, now, what about the quadrant? We know inverse tangent can either be in 1 or what? 4. Which one do you guys think? 4. Good. How did you know it was in 4? Yeah, it's the negative that gives it away. Make sense? Can you tell me what theta would be? Perfect. I think you guys got it. Make sense? Okay. All right, let me copy all this over. Let's do a few more. So same thing, find the exact value of the expression. Let's look at number 22. We have the inverse tangent of the square root of 3 over 3. All right, so again, the first thing you've got to recognize is you're looking for an angle because you're looking for the inverse. And because it's inverse tangent, you've got to keep yourself between negative pi over 2 and pi over 2. You can't include the two ends. All right, we know with inverse tangent, there's only one quadrantal available, and it would mean that your ratio here would have to be 0. And then, so it's not coming from a quadrantal. So it's either the 30, 60, or the 45. You guys okay? I know it's not the 45. Why? Because we just did it, and we know 45 is 1. So it's got to be either the 30 or what? The 60. So we've got to figure out which one. Now, if you look at 60 first, it would be opposite over adjacent, correct? Which would mean it would be square root of 3 over what? 1. But that's not what we have. Are you guys all right there? So when that fails, look at the 30. What would 30 be? It'd be 1 over what? Square root of 3, which is what? Root 3 over 3. Does that make sense to you guys? Are you with me there? Because if you have 1 over root 3, that is root 3 over 3. Yes, if you rationalize it. You guys with me? So I've determined, I think this is the hard part, that the reference angle is what? 30 degrees. Make sense? Which means a denominator of what? 6 in radians. Okay. All right, now the next important piece is, since it is a triangle, we got to figure out which quadrant. Which quadrant, you guys, 1 or 4? Good. How'd you know it was quadrant 1? It's positive. Can you tell me what theta would be? Pi over 6 is correct. Very good. Uh-huh.
So we need 2 answers or 1 answer to this question?
Huh?
Is it 2 answers or one answer?
Just one. Just one angle. That's it.
So we're looking for phases.
That's it.
Okay.
Yep. Because it's just, remember, just think about it like this. If you're trying to land a plane, you're going to know the ratios, right? Because you know where you are and you know where you, well, hopefully you know where you're trying to land. So what you're trying to do is figure out the angle. Does that make sense? And so you've got to have the inverse to kind of be able to reverse that process, because normally we plug in the angle and we get the ratio. So just think of the inverse as always giving you access to that angle. You're saying based on this ratio, this is the angle that I would need. Make sense? Okay. You know how math is. You make one thing, they always want you to be able to undo it or go the opposite way. You know, you have addition, but you can undo it with what? Subtraction. And so we always have an alternative way to do things. So if you take x to y, we can take y back to x as long as we have an inverse. So it's just how we are able to do that. Okay. All right. So now, finally, let me give you inverse cosine. So they kind of skip around. Just bear with me. We'll put it all, we'll get the two families together in just next section. We'll be able to put it all in. But we have, I told you, the other family was 1 and 2, right? And so inverse cosine will start that for us. So let me go ahead and define that for you. It is on page 611 in the book. I'm going to go ahead and just write it out since we're writing it a little bit different. So it says y is, I'm sorry, we're going to write it with thetas. So we're going to have theta is equal to the inverse cosine of x, which means you can easily go right back to cosine with the restrictions in place as long as you swap the coordinates. Meaning plug in the angle instead of having the angle as the output, okay? Now, the restrictions on inverse cosine, your domain here, I don't think you'll be surprised, is -1 and 1. Or they'll say x is between -1 and 1. And then your range is going to be 0 to pi. And it is inclusive, so you will be able to include those two ends. Now, I'm such a visual person, I never see things like that. I always see the picture. That's just the way my head works. I'm going to draw it for you guys just in case you're kind of like me. And so for me, what I'm visually going to think of is like this. And I think, okay, here's 0, here's pi over 2, and here's pi. You guys with me? All right, and so this would be 0 to pi. I know I'm moving counterclockwise because everything's positive on the angles. Makes sense? Which means what do we have available? 1 and what? 2. Notice you have 3 quadrantals. You have 1, 0. You have 0, what? 1. And then what? -1, 0. So there's your quadrantals that are available to you. Never go to 3, never go to 4. Yep. And that's the hard part, you guys, is remembering who's in which family, because you got to know the restrictions. If you know the restrictions, you're good to go. All right, everybody got it? Okay. All right. Now, let's look at some examples. It's going to be the same thing. I'm going to go ahead and visually take this picture over because I know we're going to need it, and I'll attach the 2 triangles here. Or, like I said, if you know your points on the unit circle, that is just fine. But I'll go ahead and redraw them since you're getting a little messy there. We can easily go right back to cosine right by just switching what we plug in. So that's what we're going to be looking at. Okay, so find the exact value of the expression. And actually, you know what? My video is getting a little long. Let me stop and just restart it real quickly.